In this video, we will build control unit for our 8-bit CPU. Hey guys, welcome back to the channel. Sorry I'm posting this video very late. It's been almost 4 months since we posted our last video. I was busy with my thesis and other works. That's why I have not posted in a while. In this video, we are going to build the control unit. In last video, we saw how our control unit works and what are the steps to build it. In this video, we will start to write the control unit, and hopefully by the end of this video, we will finish it. I will try to wrap up this series as fast as I can. So I think it will take another 2 or 3 videos. So if you haven't watched my previous videos, I suggest you go back and watch all the previous videos and then continue watching from this video. If you haven't subscribed to the channel yet, please subscribe and help me reach my subscriber goal. So without wasting any time, let's get started. So one more update. My Model Sim license got expired. That's why I'm switching to Vivado. I'm not going into the details of how to set up your project in Vivado. For that, there are many YouTube tutorials, many good YouTube tutorials available. Please watch them and set up your project accordingly. So let's start. We will add a new file, design source. We will call this control unit. Our control unit will have 2 inputs. No, actually 3 inputs, sorry. It will have a clock. It will have a reset pin. It will take instruction coming out of instruction register as input. As we saw in that previous video, it will be 4-bit input. So standard logic vector, and as an output we will produce a standard logic vector which is 17 bits long. These 17 bits will be nothing but our control signals that will go to all our other modules. I will explain in a bit what are those control signals. So this is our control unit entity. So as we saw in the last video, we need internal counter to count on which micro step we are. So we will need to make a counter in this control unit. So let's start with that. We will write a process for the counter. Let's count it, count process. It will take clock and reset. Okay. It's asynchronous reset, so if reset is equal to 1, then we will set counter to 0. Okay, we will need a signal counter. It will be a standard logic vector of 4 bits, so 3 down to 0. With 4 bits we can count up to 16 microsteps, but we will not use 16. Our most longest instruction takes 10 clock cycles, so we will only use 10 of those. Like we will count up to 10 maximum. So yeah. Okay. Else if rising edge, on rising edge of clock we will, here we will check if our counter is equal to 10, that is 1010. If counter is equal to 10, then we will reset the counter. Otherwise we will increment the counter. So we cannot directly increment it, so we have to typecast it. I think our counter is ready. Let's write a small test bench and test if it works. I will give it name control unit test. Okay, I'll just copy one of our old test benches. I will set our control unit test bench as a top model. I will copy the clock generation process from this test bench. Put it in our control unit test bench. Let's define this signal. What was our clock period? Okay, So this is our clock process. What else do we need? Okay, we need to define component. So let's copy our port from here. Okay. Our component is here. Now we will make an instance. Write our port map. So clock, signal to clock. Okay, we need to provide it instruction, although we are not using it. What is happening? Okay, and reset signal we will also need. Not vector, sorry, standard logic. Let's set its default value to 0 0 0 0. So reset to reset signal. Instruction to instruction signal, and we will leave the output open for now because we are not using it anyway. Okay, so let's try to simulate this. We should see our counter going from 0 to 10 and again to 0. So we will add counter to our wave and relaunch the simulation. Okay, our counter is undefined. Let's see why. Because we did not give a default value to counter, and we also did not reset, that's why. So let's give it a default value and we will relaunch this simulation. So here you can see our counter is going from 0 to 10, that is A in hex, and again to 0. So our counter is working. Now we will have to write remaining logic for our control unit. Let's close this simulation. Now we have this 17 control signals, 16 down to 0. we have to set these control signals depending on our input instruction and depending on our like what micro step we are in within that instruction. So I have taken this in this order. So first is halt signal, then we have output in and output out. That is we have a output register, so to load that we will enable output in to again output that output register to our data bus. We will assert output out, so like that, and then we have ALU operation enable to enable the ALU. Then we have and this is ALU output enable to enable ALU output. This is ALU enable to enable ALU and perform some operation like add and subtract. This is program counter enable, then program counter in to load the program counter value, program counter out to output it, memory address register in, RAM out, A register in, A register out, B register in, B register out, and instruction in and instruction out. So these are our control signals. We will set these control signals and it will execute our instruction. So like we saw in our last video, first two steps for all the instructions are same. That is fetch the instruction from memory and then increment our program counter. So in first two steps we will do this. So let's write that. So we will write it like this, data out is equal to, and we will assign our 17-bit value here. So for first cycle, that is when our counter is equal to 0, we will load program counter to our memory address register. So for that we will set program counter out byte, control signal, and memory address register in control signal. So this and this will be enabled. So these 2 bits. Oh, sorry, I'm writing this in test bench. My bad. So we will write it here. When counter is equal to 0. Currently I am having some weird problem. For some reason, if I try to do this, it takes 2 clock cycles. So that's why I have to write this for counter is equal to 1 and counter is equal to 2. We are setting same control signals. I have not yet found why it happens, but I'll correct it when I find it. Meanwhile, we will make it work like this. So now with these 2 steps, our program counter will be loaded into memory address register. Now next step is to fetch that memory location into our instruction register. So for that we will set memory register, RAM out and instruction register in. So bit sequence for that is this. I have calculated all these bit sequence in advance and now just pasting it from here. So when counter is equal to 2, else for this operation also it takes 2 clock cycles. So again we will write almost same. Weirdly it takes, and in this step we will also increment our program counter. So weirdly program counter increment takes only 1 clock cycle. I don't know, this is a very weird issue I'm facing. If any one of you guys know why this is happening, please let me know. You know, all, like, you can see on the code in GitHub, on GitHub, and let me know if you find the reason. I'm not able to find it for now, so I'm just making it work as it is. So by using setting these 4 steps, in these 4 micro steps, we will have our instruction in our from RAM. We will load the instruction to our instruction register, and we will increment our program counter as well. Now these are the common steps for all the instructions. From here we will check what is the instruction that is being executed, and then set our control signals accordingly. So our first instruction is LDA. So for that we will set now. So I'll write LDA here. So in LDA we need to load accumulator with a memory location. So we will set some control signal when counter is equal to 0 0 1, sorry, now 4th step, so 1 0 0, and instruction. So as we saw in our ISA video, LDA is encoded as 0 0 0 0, so 4 zeros. I'll put a bracket around this. Okay. Control signal to set is, we will first put instruction register like address on our data bus. Then we will need to load that address into a memory address register. So our memory will put whatever we want to load into that location. And then from memory we will add to register A in next clock cycles. Weirdly, again this operation again takes 2 clock cycles. So in next 2 clock cycles we will do the same, and that's why this instruction will totally take total of 7 clock cycles. And okay, for rest of the 3 clock cycles we will just set all control signals to 0. We will do nothing in this period. So that would be 1 0 0. And next clock cycle. So we have written this. So this is our LDA instruction. This should set appropriate control signals to load a memory location to our A register. So now we will test this instruction and see if if appropriate signals are set. So in our test bench, let's write a process. We will assert our reset signal for some time. Say 5 clock cycles. Okay, we will define a signal called control output. Uh, 17 bits, so 16 down to 0. And we will attach it to our control unit instance. Okay. One thing we can do is to define some more signals and attach them to these specific control output pin within that vector, and so that we can see like this is performing correctly. Okay. Let's just write bit numbers. Let's just write the whatever bit numbers are there in our signal, so that it's easier for us to understand. Okay. In these two steps we are loading program counter to memory address register. So program counter out, that is bit 9, and memory address register in, that is bit 8, should be set. So in our test bench we will take two signals. Program counter out, memory register in, and let's set these to control output and corresponding bit numbers. So what was for program counter out was 9, and memory address register in is 8th bit. So it will be easier for us to verify this. So just let's launch this simulation. So here you can see our program counter and program counter out and memory address register in are set for 2 cycles, as we and then again while loading instruction, our memory address register in is also set, and after all these steps are finished basically, then again because we don't have any instruction now, so it's resetting. So again here you can see for 2 clock cycles these 2 signals are set. So our control unit is working now. So I will just I have written I have written microcode for all the other instructions already. I will just paste it here. I will not explain each instructions. So if you want to know what happens in each instruction, you can watch my previous video. In that I have explained what micro steps are there in each instruction, and then if you want, you can verify like all the control signals. So I will just now paste all the microcode here. So this is the microcode for remaining instructions. So this is LDA, then STA, add, subtract, jump, out, and halt. I have tested all these instructions and they are working fine. So you should also try to write this control unit, and let me know if you have any errors or doubts in this. I have tested this and it works fine. Do try out this control unit, and that's it for this video. Please let me know in the comments if you have any issues while doing this implementing control unit. In the next video we will put everything together and try to finish our CPU. After that we will take a few sample programs, and I will walk you through the simulation of those programs and how it works. So thank you for watching this video. Please subscribe to the channel for watching more videos like this, and see you in the next video.